for us to think about is going to be the nature of the leaving group. We're going to think now about the nature of the leaving group. This is a new entity for us that we have to consider. Please be very careful not to confuse leaving groups and nucleophiles. They're going to look similar at times. The nature of the leaving group, the nature of the nucleophile, and what makes a good leaving group and what makes a good nucleophile are different from one another. So please study these in the order I'm presenting. Substrate's number one most important thing. Nucleophile is important to understand. Leaving group is the third thing we're talking about. Let's actually just practice this reaction now. We're going to do 3 analogous reactions. We're going to react hydroxide with methyl iodide, methyl bromide, and methyl chloride. We're going to rapidly practice this mechanism 3 times in a row. So when it comes time to the exam, none of you can say that I didn't teach you this and that you didn't practice it. We've already practiced it 2-3 times today, but we're going to practice it 3 times in rapid succession. This is our substrate, polarized bond, plus charge, right on carbon. Nucleophile doesn't have a carbon in it, easy to identify, negatively charged, lots of electrons. The reaction happens in rapid succession. Nucleophile attacks substrate, leaving bond breaks, and we now have something new here. In each one of these cases, we made the same product, methanol. And the leaving group, however, was different in each one of these cases. We had I minus, Br minus, Cl minus. These 3 reactions all take place, but they happen at very, very different speeds. Turns out iodine is much faster than bromine. Bromine is much faster than chlorine. Most reactive or fastest, slowest. And the trend for the leaving group ability, students do get confused, so please study the nature of the leaving group and the nature of the nucleophile separately. But the leaving group trend is based on basicity. The weaker the base, the better the leaving group. So weak bases are very, very good leaving groups. Weak bases are very, very good leaving groups. If ever you're unsure, you can always look to the conjugate acid. If you're ever unsure about whether you have a weak base and a good leaving group, you can always look at the conjugate acid. HI versus I minus. HI, if you know, is a very, very strong acid. Based on the periodic trend, then you know that this is a weak base. And therefore, a great leaving group. Okay? So if we're really not sure about a species we see as a leaving group, we can always think back. Well, I minus. Is it a weak base? I don't really remember. Maybe you remember the periodic trend for this, but if you don't, you can always look at its conjugate acid and say, oh, this is a strong acid, and this must be a weak base, and the trend for leaving groups has to do with basicity and weak bases. We're going to put a list of common leaving groups that we encounter all the time, and that we're going to encounter all the time in this class together, just to give it an understanding of this particular trend. So we're going to draw OH minus or OR minus, where this is an alkyl group. Okay? So this is one type of potential leaving group. Then we have F minus, Cl minus, Br minus, I minus. And there's going to be another group that we learn about called tosylate. So we'll call tosyl minus for now, or tosylate. We'll draw it in a minute, right? So these are going to be our very, very common 1, 2, 3, 4, 5, 6 leaving groups. And the I minus is very, very common, so is Br minus and Cl minus. We'll learn about tosylate in a minute, but we know that this is a weak base. Still weak base. Now we're getting into less weak bases compared to these. And these are strong bases. And poor leaving groups. These are great leaving groups over on this side. In fact, these strong bases are such bad leaving groups that when they're attached to a molecule, there will be no reaction possible with these types of leaving groups. We'll practice this many, many times, don't worry. First, we're going through these 3 or 4 criteria or considerations, and then I have a series of examples we'll spend time working on, slowly thinking about each one of these things one at a time. Okay, so it's a little overwhelming right now, these trends, but they'll be easy to digest and apply in our second half of our lecture today. Let's talk very briefly about tosylate. We'll come back to it. I wrote it terribly here. But tosylate. Its name? Tosylate has this particular structure. It's para-toluene sulfonate. Okay. This is a benzene ring. This is a methyl group. And this is called tosylate. And to be a good leaving group, it has to be a weak base. So that means this is a very weak base. And then let's look really carefully at its conjugate acid. This species right here is a very, very powerful acid. Does it remind you of any acid you know or have seen before in this class or any other class? It should remind you a little bit of sulfuric acid. Sulfuric acid is a very, very powerful acid. And this particular molecule is an organic version of sulfuric acid. We just replace an OH group with this toluene group. Makes this particular compound a solid. This one's a liquid, so you can measure this out on a balance. It's very easy to measure out with a spatula. And the functional group that's important here is this one, the sulfuric acid group, and this is not called sulfuric acid, it's called sulfonic acid. And if this is a strong acid, then this is a weak base. And we're going to use this particular group tosylate in the future to do something special with. You'll see it's very, very simple. But I just want us to recognize right away its relationship to sulfuric acid, being strong acids, it's being a weak base. And so it fits somewhere in this spectrum here of weak bases. The most common leaving groups we're going to see are right in here, these 4. We have the whole periodic table to use in any sort of base, but these are the ones that are always used. These are the ones that are always used in these SN2 reactions. We're going to see Cl, Br, and I used extensively in these types of problems. And as you saw in our pre-lecture video, that we can take one substrate and react with a whole variety of things to make all sorts of different products. And this particular series of leaving groups are these common things. We can substitute these, if they're attached to a substrate, for any number of nucleophiles. So that's going to be a point where we're going to take a break here. We'll take a break just 7 minutes today. We'll go to about